Hey guys, welcome back to the Beginner's Guide to Restoring Early Tube-Based Black and White Televisions. Last few installments focused a lot around this lower power supply chassis, how to replace the electrolytic caps, how to replace the paper caps. Well, meanwhile, topside, an interesting little phenomenon, a little issue has cropped up. I think you're going to find an interesting topic to take a deep dive into. So, that's what this installment's going to be all about, taking a look at a problem with one of the tubes on top. Well, I just noticed a little phenomenon that's probably been happening for a while. It just didn't catch my eye. I want you guys to keep your eye on this tube when I turn this set on, and we're going to do this in subdued lighting. See that blue flashover in there? Yeah, that's not good. So far I've been focusing my testing, my demonstrations on this side of the power supply, the bigger power transformer, the 5U4 filter choke, and the dual 40 microfarad cap. This is the one we tested. It was leaky, but not horribly so. I haven't checked this one at all. So this could be really leaky, and it's drawing a lot of current from that tube on power up. But there's another very good potential issue too, is that I removed the speaker field coil and substituted a power resistor for it. The field coil was around 700 ohms DC. I put a 1,000 ohm power resistor to substitute because I don't want to damage the speaker. I don't want to have it flopping around on the workbench. These don't work the same as inductors. Inductors resist a change in current. Capacitors resist a change in voltage. Inductors resist a change in current. A power resistor is not the same. I used a larger value hoping to compensate for that. I don't think I went large enough. That's a possible issue. We can test that very easily by plugging the speaker back in temporarily. If we still get flashover with the speaker installed, we know we definitely have a problem downstream of this tube. Another remote, less likely possibility is this tube could be bad. It could be gassy inside, or it could be have some other problems in there, but I suspect it's one or the other. So let me grab that speaker and give it a try. Okay, speaker reinstalled. Everything's cooled down sufficiently. Let's try another test. And here we go. Still has that blue flashover. Alright. Good and bad. Bad in that we gotta do something about it. Good in that it looks like my substituting a power resistor isn't really the issue. So, we're going to do two things. We're going to test this. We're going to replace it. And while we're replacing this, we might as well do that. So, time to drill out some rivets, disconnect some wires, get those caps going, and all that. Hang on now. Let's not get carried away. I've seen something like this before. It might not be what it seems. It might not be a bad cap. It might not be excessive current draw. Let me redraw the schematic up here on the whiteboard, simplify it a little bit, break things down a little bit, and let's see what's really going on. I'm going to go right to the secondary of the power transformer. Center tap, going to ground. What does that secondary go to immediately? It goes to our 5Y3 plates, and cathodes coming off. They are internally connected. What does that go to? So this is our 5Y3 here. What does that go to immediately afterwards? Which we presume might be causing the flash. It goes to a capacitor. One of those sections of a can, electrolytic, going to ground. What is the value of that cap? This is important. It is 60 microfarad. What comes after this? It actually goes into two paths. One is actually a power resistor. If you recall, when we were looking underneath this chassis, there's a big old power resistor down there. That's where this comes in. It's a 3.3K 2-watt power resistor. Other side of that has another one of these, electrolytic, another section of that can. And this time it is 40 microfarad. I was thinking, hey, wait a minute. Well, what about the field coil? So the field coil matters. Yeah, well, one, this explains why I still saw a flash when I didn't have the speaker attached. There is still a load. There's actually two paths. I didn't realize that when I was initially analyzing this. The other path goes up to the field coil. So if the field coil was to fail, the speaker wasn't there, some power would still get through. I imagine it's going to be degraded, probably going to be some issues. And this goes to yet a third electrolytic, but this time it's only 20. So 20, 40 is 60. And this, of course, is positive. This goes off to stuff. This goes off to stuff. I don't think these connect together. No, it appears they do not. So they serve different loads, different purposes. Alright, similar to what we analyzed earlier, just a little bit different in that there's two paths it can take at this point. But imagine this stuff is in here just like before. We have our half-wave rectified DC. We put this stuff in, we end up with DC with a little bit of ripple. You get to either side of this with the additional filtering, and we basically have pure DC coming out here. All right, let's talk about what happens when the set is cold, discharged, and you first turn it on. Well, if you watch an ammeter and look at the current, say this is 0, there's an initial big surge. That is the tube filaments. Cold tube filaments have a much lower resistance than hot tube filaments. So there's a big current draw when you first turn it on, which fairly quickly drops back down. That's from the tube's filaments. Big surge, they heat up, their resistance goes up, the current drops off. Until the tubes start conducting, or until they warm up after a few seconds, they don't conduct any current. So unless we had some resistive load in here, the tube circuits downstream really aren't drawing any current yet. The two rectifiers, the 5U4, the 5Y3, are directly heated. They don't have a separate heater and cathode. The heater and cathode are one and the same, so they heat up faster than the other tubes. What happens? So our tubes down here aren't drawing power yet, but what do we have right after this? A cap. These are discharged. As soon as these heat up and start conducting current, it's going to charge up the caps, and this cap, and this cap. So there'll be an initial surge from the tube filaments, and then very quickly there'll be a second surge. Sometimes they're kind of blended together, so it's hard to separate them. That's the caps charging up. Which happens pretty quickly, and things drop down until the other tubes in the set warm up, and then this goes back up. And then it'll stay steady as the set's operating. Alright, there's two basic ways to make a power supply filter back in the tube era. If you look at a tube manual, which we're about to, they mention two types. One they call a capacitive input filter, one they call an inductive input filter. This branch is a capacitive input filter, meaning the first thing we hit is right after the rectifier, it goes right to a capacitor. Then a resistor, then another cap. It's a pi filter, but with a resistor. Now this top half is also, it's a capacitor, then an inductor, then a capacitor. So it's still a capacitive input filter. But imagine we designed one that didn't have this. And we just had, right after this, we had a resistor or an inductor, and then a filter cap. Well, they don't talk about an RC, but they do talk about this, and they call would be the choke input filter or inductor input filter, meaning the first thing you hit is a choke. It matters. There's a big difference. A discharged cap looks darn near like a dead short, and actually the better quality cap, the lower ESR, the higher the ripple current it can handle, the more this looks like a dead short when you turn the set on. So actually, in terms of there being a gentle startup, having a degraded capacitor actually puts less strain on this tube. So what could cause it to flare up like that? Well, if this was a dead short, yes, that would be a problem. Or if you put it in a much larger cap than was there, it would look like even more. Imagine it's like an empty bucket that has to get filled. The larger the bucket, the more goes in there to fill it up. Once it fills up, the current draw stops. Inductors, even if this was a dead short, these resist current flow. So these inherently are a gentle startup. It takes the building up that magnetic field in a choke takes a little while. So these, a choke input power supply is gentler on the tube than a capacitive input filter. So why do they ever use a capacitive input filter? Well, there's downsides to doing this too. One thing, when you turn it off, that energy collapses and it's got to go somewhere, so you get inductive kickback. Also, they're big, they're heavy, they cost more. So more typically you see capacitors and filters, and if they have a choke, it'll generally be on the more modest side. You go to much earlier sets, they didn't really know how to make good electrolytic caps. They might only be 2 or 4 microfarad for really early caps, and they have ginormous filter chokes. So it comes down to really is cost is a big factor. All right, so let's focus back on this. Let's look at the tube data for 5Y3. There are scan tube manuals available online if you don't have one. By the time this is an edition from the 60s, and by then the 5Y3 was kind of obsolete, but it is still in here. All right, now they have 2 sections down here. As most of these tube manuals do, they'll have charts and numbers and descriptions and maximum ratings, but then they'll give you typical ratings. So typical operation with capacitor input to filter. That's what we have. And they show 2 design styles or guides, one with 700 volts on our secondary, one with 1,000. What they mean is a cross here. So if it's 700, to be 350 on either side. By the time you get through all this, the output might be, there'd be drops, there's losses in the various circuits. You might get 300 out at the output or something in that order. So that's sort of in the ballpark of what we have. We have even less than that, actually. All right, so let's just go with the 700 column. It's the closest to what we have. Filter input capacitor, 20 microfarad. Now, they don't list it under the maximum. They just have typical design value. 20 is a lot less than 60. What is the maximum? In other words, as I said, the larger the capacitor you use, the more it takes to charge up. When you turn this on, you get a current surge going this way. Tubes have a maximum amount of current they can safely have go through them. When you exceed that, you see things like a blue glow or a flashover where it could actually arc between that. That's what we're seeing. We're seeing a surge when you turn it on. Is 60 okay? I did some more research. Some anecdotal evidence online, some inferences from other tube manuals or flat-out statements in other tube manuals. It seems like the safe maximum is around 30 or 33 microfarad, about half of this. So for whatever reason, when they designed this, They used a much larger capacitor than this tube can safely handle. Now let's take a look at that. It does say 5Y3 GT. There might be other versions. It might be a 5Y3A, a 5Y3B. They can handle more. But this is old. This is old school. This uses the base original 5Y3. It can't handle 20. Sorry, I mean it can't handle 60. This should be 20 or 25, maybe 30. But I would go with their recommended guideline and put a 20, or these days a 22 in there. Why did they go with 60? I don't know. Now, another possibility is that the capacitor they originally used was so lousy, it had really high internal resistance, which provided a soft start. I doubt that. I doubt that. I think it's just a bad design. And I've seen this before in other Admirals I've worked on now that I think about it. And I've modified the circuit to take it into account. So what can we do? Well, if you recall when we originally got this, it didn't have a 5Y3. It had a 5U4. So maybe whoever poked around this set knew a little something about a little something and put a beefier tube in there, because the 5U4 can handle more. Let's see what it says for that. The other option is, well, you could put a smaller capacitor in there, or we put some type of current limiting device in there. Let's see, 5U4, they show a typical capacitance of 40. And that's what we have on the other side, where we have a 5U4, we have a 40 microfarad. So they actually put a larger cap on the weaker tube. I think a 5U4 could maybe handle 60 just. But really, this should be a 40 with the 5U4 and a 20 with the 5Y3. So we could reduce this to 20. Potentially, though, that won't be enough filtering and we'll get more ripple down here. What we could do, though, is increase these, because we have some current limiting inherent in this resistor and this choke. So we could reduce this guy and increase both of these, make this a 60 or an 80, make this a 40 or a 60, and make this a 20. That's one way to do it. Another way to do it is to put current limiting in here. Put something here. Put a thermistor. Put a resistor. You'll lose a little bit of voltage if you just put a fixed resistor in there, because there's going to be some drop across it. What would the resistor value be that's appropriate? I don't know. 100 ohms, 50 ohms, 220. That'd probably be too big. You don't want to drop too much. You want to have enough that you don't get that flashover, but not so much that it gets super hot or limits power to the rest of the set. Maybe 10 would be enough. I don't know. So I mentioned I'd done some stuff before to help it. I think I put a CL90 thermistor in there, which is a cold resistance of 120, and when it's hot, it's more like 5 ohms. So that's one possibility. Putting a thermistor, though, in a B+ supply is kind of an odd application for a thermistor. I think a fixed resistor would be more applicable. So we could experiment with that. I'm kind of more inclined to change the capacitor value, though, and make this a 22 or a 33 and bump these guys up. I think it might be less confusing to somebody down the road, too. Rather than adding additional parts, we're tinkering with the component values and caps we're going to be replacing anyway. Right here now, what am I going to do? I got to think about it. First, let's at least check this 60. And for now, I might just tack a power resistor in there, because I want to move on to some other stuff before I go about drilling out and replacing these caps. But that's what's going on, I do believe. And we can very quickly test that also by adding a series resistance in here. I'll put... let's start with a 10 ohm. And let's see what that does for us. And I'm just going to do this by observation, by looking at the tube. That doesn't, just because the tube isn't flashing over doesn't mean it's necessarily still within its safe zone. So if a 10 works, we still might want to go to 15, 18, 22, something like that to get even more cushion in there. Here's that 5Y3 socket. I cut a wire coming off from the tube that's going to the filter choke into that cap. and threw in a 10 ohm resistor. I don't really need this resistor going to the field coil, I just need to go into the cap, but this is a really convenient place to tack it in there. Alright, let's see if it does the trick. Alright, focused on that 5Y3 again. There's a test with the 10 ohm in circuit. Here we go. Nope, still had a blue flashover. Let's go bigger. Let's go 22. Yes, this is where one of those decade boxes I showed in a recent video would come in handy. Alright, here we go with 22. Nuts. Alright, let's just jump right up to 100 and then we can work our way back. Let's eliminate it completely first. Let's try it again with 100. I really think changing the cap value is the right way to go, but anyways, here's 100. Still there. Alright, stop screwing around with adding a series resistor. Well, actually two things. One, let's just do it without a resistor at all, with nothing attached to the tube, because I'm a little surprised at 100 it's still an issue. Then we'll try disconnecting that cap. Alright, just to verify that this is the issue, here's a test with no load on the tube. I disconnected it from anything else, just filaments. Here we go. Power up. Alright, no blue glow. Okay, I'm not losing my mind. Let's disconnect that 60 entirely, and I'm going to hardwire this back up the way it was. Alright, I wired everything back the way it was originally, but now I've disconnected the 60 microfarad filter cap. Let's see if there's any flashover. Here we go. No. Excellent. Alright. Here is what I propose. I am going to tinker with the capacitor values and use 20 or less for the first cap. I think I will also add a thermistor for the entire set. The set was designed to run on 117. We now have more like 123, 125 at the wall outlet. Also, it would be nice to give the whole set a little bit of a soft start. This thing draws about 2 amps. So there's quite a bit of current, meaning the thermistor is going to get pretty hot. We should probably choose one that's rated for 2.5 or 3 amps to get a little bit of overhead, and then mount it away from everything because it's going to get warm. But that will give the entire set a little bit of a gentle start. One other thing we could do is put the 5U4 back in as well, or find a beefier equivalent of a 5Y3, a 5R4. So there are other rectifiers out there. But really the problem... Now, why did they put a 60... Really the problem is that 60 microfarad being too big. Why did they use a 60 in the first place? A 5Y3 is really just an 80 in a different package. So it had been around for a long, long time. And its characteristics were very well understood. I have no explanation for why they would do that. The vast majority of TVs I've worked on use a 5U4 and they use 40 microfarads for the first cap. Why would they would use a larger cap with a lesser rectifier tube? I don't know. If any of you have any thoughts, I'd love to hear them. This took a lot longer than I thought it would, but I think this issue really deserved an in-depth exploration. This comes up all the time with tube amps and radios and whatnot, seeing a blue glow on power up. That's why. There's a heavy load. And they can even just be putting, maybe the original design was all right, but you put really high grade caps, have a really low ESR in there. Now you're putting actually more of a load on your rectifier, and you could be doing maybe a little more harm than good by putting in super high grade fresh capacitors. So adding a thermistor to basically any tube electronics is not a bad idea if it's properly rated and mounted correctly. They do get hot. There are a wide number of ratings in terms of how much current and their cold resistance, their hot resistance, and all that. Generally, a CL90 is the go-to for this stuff. It's 120 ohms cold, around 5 ohms if you've got 2 amps running through it. If there's 1 amp running through it, it's more like 7 or 8. Less than an amp, it goes up even more. Seeing as how this is a little over 2 amps, I'm a little hesitant to use a CL90. I'll see what I've got. I may have to order up something that's a little beefier, or put 2 in parallel, I suppose, would work too. I monitored the current draw of the whole set more closely, and it's only about 1.5 amps. I think the higher current rating I saw in the service info was for the combo set, which has a radio and a beefier audio output stage. So a CL90 will work just fine. It's simply a matter of mounting it somewhere. Ideally, it'd be on top of the chassis in free air, but that would involve drilling holes, running wires, adding a terminal strip. I think we'll be okay underneath the chassis. Find an area that's not near anything else, and try to get it near a side of the chassis so that can act as a bit of a heat sink for it. Plus, I'm not planning on running this set for hour upon hour. But we'll see how it goes. I'll add it in a bit, and I'll monitor it and see how warm it's getting and see if it's affecting anything nearby. I don't think it's really a big concern. Alright, that's going to be it for now. Next, we'll move on to working on the main chassis. We got a whole lot of stuff to do.